Hello, everyone. Thank you for attending today's webinar, Analyzing the Selection Criteria for Image Sensors in Your Design, presented by onsemi. I'm Jenna D'Angelo, and I will be hosting today's webinar. I'd like to start by introducing our speaker, Steve Harris. He's the Senior Director of Marketing, Industrial and Commercial Sensing Division at onsemi, and you can read his full bio on the left side of your window by selecting the Speakers tab. Just a few notes before we begin. You can access closed captions from the bottom right corner of the video player. This webinar is being recorded and will be available to watch on demand within 24 hours. We'd love to hear from you. During the presentation, please submit any questions you have using the Q&A tab on the left side of your screen. Time permitting, we will conclude with the Q&A session. Okay, now let's begin. Steve, I'll turn it over to you.
Yeah, thank you for that introduction, Jenna. Appreciate it. So maybe just a quick introduction for everybody to myself. My name is Steve Harris, and I'm the Senior Director of Marketing for Industrial and Commercial Sensing Division. I actually have been doing imaging now for almost 12 years. Actually came through the acquisition of onsemi, Aptina by onsemi. And was doing industrial kind of commercial type stuff when I was at Aptina, switched into automotive, did a lot of automotive ecosystem, kind of came back to industrial and commercial sensing. So really I've kind of seen the broad spectrum of the different applications in imaging. And yeah, so that's kind of a quick introduction to myself. Before we get started, I just want to give everybody a trigger warning here as a joke kind of, but the selection criteria you're about to see is going to remind you of the overwhelming amount of parameters, functions, features, considerations that you have encountered probably when you're attempting to design with image sensors. So proceed at your own discretion. And I think this next slide really proves it. So here's here's all of the selection criteria. I've been doing this for 12 years, and I have to say, I feel like I still learn something every single day. There's a lot of selection criteria here on this list, obviously, as I show you. And funny enough, as I look at it, there's probably a lot of terminology here that's even missing from this that probably go into the selection criteria. And we have about 50 minutes here of me talking and about 10 minutes of Q&A. So I think it's highly unlikely we're going to get through all the issues here, but we'll try to touch on most of them, at least a little bit to help. And then, of course, we'll throw it over to a Q&A. So in addition to kind of what I prior just showed there with a lot of different selection criteria, one thing, I'll say this, and I don't know if it's controversial or not, but my experience in the semiconductor industry, I believe that image sensors have to be maybe the most complex of all of the different semiconductors. And if you take a look at this is actually really a cross section of what an image sensor truly looks like. You have the cover glass sitting on top. Beneath it is what we have the micro lens that focuses the light into the pixel. You have a color filter array, we call it the CFA, that sits right beneath the micro lens, and that allows us to get color or monochrome or different things that we want in terms of the color spectrum into the actual pixel itself. You have the pixel wafer, and then beneath that, now we've moved to kind of a hybrid stacked architecture. I have a slide on it a little bit later, but basically all of the non-imaging related functions traditionally have set around the image sensor. For the sake of space, now they actually are on a separate wafer that sits beneath, and most of the image sensors have moved to that technology. So not only is the complexity with all of the different selection choices that you have, but even just the device that you're using is one of the most complex semiconductors that really are out there. So having said that, I do want to give a little bit of background about onsemi and our imaging heritage, kind of our qualifications for talking about this broad topic here. So we really are the combination of three different companies in the imaging space that really kind of date back to the heart of imaging. So Kodak, which became then inevitably spun off into TrueSense Imaging, and this is like literally the very first digital camera. We have people with patents that literally have done the Bayer patent that are from our line. IMEC, which turned into the Cypress Semiconductor, Fill Factory Cypress Semiconductor line, and then came into onsemi. This was about 2012, or sorry, 2014 time frame. No, 2012 for that. Sorry, TrueSense 2014. And then I came in through the Aptina line, which dates all the way back to NASA Jet Propulsion Laboratories, Eric Fossum, the very first CMOS image sensor. And all of these kind of came together around, let's say, late 2014. So we've been together now for 10 years. And then recently, within about the past 3 or 4 years, we actually added LiDAR into this. So if you look at kind of the DNA for us, we have this really large patent portfolio and a real diversity of types of sensors that we've developed. And of course, going with the different types of sensors goes into the different types of applications. So I think we have a pretty good broad view of the way the market is, and all the different devices within that market. So, kind of going into the agenda here, there are really three key areas that you look at when you're really trying to figure out what image sensor you want to use. The first one is kind of the classic one that I think everybody thinks about, and this is your lighting, your fast motion, or your frame rate, the distance at what you need to see an object, the temperature. And when I say temperature, I mean color temperature, actually. So, different types of lighting, whether it be sunlight or indoor lighting, they all can kind of produce different results. In addition to that, I'm showing traffic signal there. LEDs are now one of the key lighting devices, and so this presents some challenges for imaging. Image sensors are now doing depth. They've been doing depth for a while with stereo imaging. We're now getting into this technology we call indirect time of flight. I'll talk a little bit about it here, but this is just another area. Of course, the color and color reproduction, and then the sharpness, we call it MTF, or modular transfer frequency. So these are all kind of the traditional areas that you look at. In addition to that, of course, and I think this is more kind of transitioning into the product area, not so much the imaging side, but these are obviously complementary functions and extremely important to the design. So you have the actual physical size of the device. You have the type of package. There are many different CSP, BGA, PLCC, CLCC types of packages that are out there. Of course, power is a critical element in the choice. Just the device and the temperature with which it operates, depending on the application. Features that we can embed inside the actual image sensor to optimize the overall system. The interface that we use to talk to the system on chip, or the ISP, or whatever we're communicating with. Schedule, of course, is a critical element, and then the big one right there is the price too. So these are the kind of traditional areas that you look at, and then there are kind of the elements that I would say you can't really put a dollar value on, but they're obviously critically important. And this is kind of the tools and documentation, your support. Is the device available? How does the supply chain look? Is it reliable? Is it going to last over the life of the product? Are they working with ecosystem vendors? And the family scalability, what I mean by that there is that a lot of sensors are based off of different architectures, and therefore you have to relearn every single time you go through a new sensor with a different architecture. Hopefully you can get some scalability there, because that way you're able to apply your resources more efficiently and not having to relearn a product every single time. So these would be the three areas that I'll get into. Suffice it to say, again, in 50 minutes, of which 10 minutes are almost gone, 40 minutes, I'm not going to be able to cover everything here. And of course, we've got a wide audience, so I may be speaking to some people at a higher level, and I may be speaking to some people who may not have seen some of the content, so it is a little bit diverse too. Some really technical things, and some things also just kind of at the higher level. And finally, we'll wrap up with about 10 minutes of Q&A. All right, so just jumping into imaging performance, this is kind of one of those high-level areas that a lot of people watching here may already aware of, but for those that aren't, it really starts with what the actual spectrum of light is that we're looking at. The image sensor, kind of represented in that pink line there, is really sensitive to areas that are in the ultraviolet range, which is on the kind of lower wavelength side to the left there, more of the blues, all the way out to the near what we call near infrared, literally the infrared that is not visible by the human eye, but is certainly visible by the image sensor. There are technologies, by the way, too, I'll just mention this, that actually stretch that for the image sensor that can allow it to go into shortwave infrared or even more specifically focused on ultraviolet light. So that's just kind of the very high level. And then this is a slide I think, again, a lot of people in the industry have seen, but for those who haven't and really just want the top level knowledge of how the imaging works, basically you have the pixel top is what you see, the micro lens. This is focusing the light, as I'd mentioned, to get into the actual sensor. You have the color filter array, and this is so we're filtering out for different colors, and then we can do a color reproduction. And then you have all the circuitry associated with turning, you go photons to electrons and then electrons to, voltage at some point. So this is all that circuitry. And then there are other complementary types of functions that we do as well. The industry for a very long time was doing this with what we call the front side illuminated technology. And this is where the photodiode actually sat beneath the metal layers. But I would say probably 10 to 15 years ago, at least 15 years ago, probably at least, they moved to an architecture called backside illuminated. This is pretty much where you're going to see all of the image sensors nowadays. And this is actually the kind of a flip of what you see here on the left, and the photodiode sits at the top. And what that allows you to do, obviously, is now you're closer to the light. You don't have to go through all these routing layers. And it just allows your device to be a lot more efficient. You can isolate the pixel better. And then the latest technology, which has been around, I'd say also for probably close to 10 years, but really I think just prevalent now, is that there are actually two wafers. As I mentioned before, you have the wafer that is doing the imaging related functions. And that's basically the pixel that you see there and the wiring around it. And then you have all of the other complementary functions that sit beneath it. And what this allows you to do is to optimize the size. So this is a trend that has not changed. I mean, we're still at the BSI wafer stack. I know people are looking at other types of ways of doing some stacking. But at the end of the day, what it all comes down to is what we call the fill factor. And this is really the conversion of those photons into electrons and how to do that best. And that's just something that's not going to change regardless. And there may be different architectures to do that, but that's really kind of the heart of it. So really in the selection criteria, where do you start? And I think really the answer to that is it all really starts fundamentally with the resolution, the pixels, and the optical format. And I think more even specifically the optical format. The optical format is really a representation of the size of the actual sensor itself. So the bigger the sensor, of course, the more light that you're able to capture. But the bigger the sensor at the same time, the more the cost is. And by the way, it's not just the sensor cost, but it's actually the cost of the optics above it. So you hear formats like 1-inch format all the way down to 1/3 inch, 1/4 inch, 1/5 inch. And then off to the right, here's kind of a chart showing your resolution, your pixel size, and your optical format. And the dilemma that we have here is that if you keep the same resolution in a different optical format, what it means is that in the larger optical format, you have a bigger pixel. In the smaller format, you have a smaller pixel, of course. The bigger pixel, again, able to capture more light. So if you have a higher resolution in a bigger optical format with a bigger pixel, better than, at least performance-wise, than doing in a smaller size, but at the same token, there's a cost trade-off. And this is always kind of the big dilemma in the imaging industry, and why on the prior slide I had said that really the pixel technology at the heart of it is kind of the key thing that is continuing to improve. And that's because we want to continue to get devices smaller, more cost efficient, and still give you the same kind of performance that you were able to achieve when you were at a larger device. So this is really kind of the heart of everything. Now, in terms of selection criteria, the first one that comes right out is just the low light. Are you good at imaging in extremely dark conditions? And in the case here, this is just a 1 lux image that we took, a very, very low light image, practically no light. And you can see differences between a smaller pixel on the left and a larger pixel on the right. Your goal is really inevitably to get the smaller pixel on the left to look like the larger pixel on the right. So I'm not going to speak too much on this because that's really at the heart of it. What the low light improvement is. It's just at the end of the day having a better pixel. There are some other techniques that you can apply, different color patterns, etc. But at the heart of it, this is really what's going on. It's a pixel size selection and just pixel improvement. Now, the area I think though that probably has the most differentiation and consideration um, is really the high dynamic range. And I think more and more the market is moving to higher dynamic ranges. So at the very left end of the spectrum, 10 to the minus 3 here is really a kind of starry night, not a lot of visibility, all the way to the right where you just have high sunlight. So this range is literally covering over 150 dB. So what you obviously have to look out for here is, where am I? Am I outdoors? Am I indoors? Am I indoors, but I have sunlight coming through a window? This is kind of the high dynamic range issue. So classic case here, high dynamic range imaging. You want to be able to, at the same image, see the low light, also be able to see in the highlight area. And the image that I'm showing here on the left, a linear image, is what we call a non-HDR image. HDR image to the right. And you just see, obviously, that you get a lot more visibility and clarity with the HDR image. Now, applications outdoor, I think, certainly have pushed HDR to better and better technologies. But, even things like my web camera right here on my notebook, if I were to point this at a window right now, in the back, it'd probably wash out my face, right? So not every application has moved toward having higher dynamic ranges, but I think more and more it's becoming more critical. There are 3 different approaches, and this is why I want to spend a little bit more time on this because, low light, it's just getting better pixel, but there are different approaches to how you do high dynamic range. So the one way would be in the spatial domain. I'll kind of show that in a picture on the next slide here. But this is really where you're doing different things with the photodiode to collect different kind of exposures. There are things that you can do in the time domain, which means maybe you're taking multiple images with multiple different exposure periods. So you have a high exposure for a very long period of time and a very short exposure, and you combine those because now you've got the highlight and you've got the low light. You combine those and you get the image. And then the final one is, hey, can we just make our photodiode bigger? Or can we make the linear full well of the photodiode bigger? And in that case, right, you don't have any issues in the spatial domain. You're not, modifying the size of the pixel, and you don't have any issues in the time domain because you are, not taking an image at a different point in time. You're just allowing your pixel to expose for longer. So this is kind of an actual physical representation of HDR imaging. So multi-exposure approach, still popular here on the left. And to be honest, there are some disadvantages to this, but it depends on your application. So this is the case where you take 3 different exposures. You have an exposure here where you are getting the highlights, you're getting the midlights, and then here you're trying to do your best for a longer or shorter exposure to get the low light and not to oversaturate. And then you combine the 3 images. So the benefit of this, right, is that you have a lot of controllability over how many exposures you have and what the ratios are between those exposures. The problem happens is because you are doing this sequentially at different periods of time, that if you have a lot of motion, that third exposure, second exposure are going to be different from the time of the first exposure. And so it's going to introduce motion. And I mentioned light before. A challenge with this type of approach is LED flicker. The LEDs in lighting flicker because the image sensor is effectively capturing for a period of time and maybe not capturing for all of the frequencies and duty cycles of the LED. So multi-exposure approach, if you don't have LED lighting, you're not concerned about it, good approach. there does require obviously some circuitry to combine those exposures into one. The middle approach here is a split diode pixel approach that we actually patented, I think, also about like 15 years ago. We don't really adhere to this one ourselves too much because of some of the downfalls of it. But this is where you actually are able to control your dynamic range by having a smaller photodiode next to a larger photodiode. And so you have some sort of ratio between the light going into that, and then you produce an HDR image. Now, because of this, you're losing light because you're not perfect here in the way that the lenses are focusing here. You get color artifacts potentially because of that, and you're still susceptible to LED flicker. So the final approach, and I think this is the trend where the market is going, is what we're calling the super exposure. And this is where you have an extremely large full well capacity pixel that is done by effectively adding a capacitor next to the pixel to increase the charge that it's allowed to store. So now you really extend your dynamic range out by doing that and having a really large full well capacity features, because you can actually expose that pixel for a long enough period of time. You're able, without oversaturating, you're able to account for all the different LED duty cycles and frequencies. So this is, I think, the approach that the market will inevitably move to. Having said that, though, there are obviously cases for the other two. The multi-exposure, I think, still being really the most popular. So that's kind of the trend there in dynamic range and kind of the approaches that you see. So the other area is dealing with motion. And you have two types of architectures of sensors. You have what we call a rolling shutter sensor, and we have a global shutter sensor. Again, I know that for some people this is pretty high level. For some people, just maybe stick with me here. But a rolling shutter sensor, effectively, the way it works is you expose a row of pixels, you read out a row of pixels. You expose a row of pixels, read it out, and so on and so forth. But what that means is that the first row that you expose is going to be at a different time than the last row. And because of that, if you've got a fast moving object, like in this case, a train, a bullet train, or you've got the fan here, because the last and first row of pixels have a time difference between them, what you're seeing is motion artifacts because of that. Now, global shutter is a little bit different here because the readout structure may be the same in the sense that you're sequentially reading out rows, but the exposure for all of the pixels happens simultaneously. So what that means is that there needs to be what we call a storage node that sits next to the actual photodiode itself and can store that charge until the pixel's been able to read out. So the result of this is that you don't get any motion artifacts or limited motion artifacts, and all your pixels are exposed simultaneously. Now, the drawback of this approach, however, is the ability actually to be able to store that charge while the pixel's not being exposed is done by, as I mentioned, a storage element that sits next to the pixel. And what that means is that you are effectively taking away a little bit of space away from the pixel. And secondly, if you want really, really small pixels, you may just not have the ability to do it because of size constraints. So you'll see a trade-off in global shutter with sensitivity, quantum efficiency, high dynamic range, but then of course, you're dealing with motion better. Now, the second argument for global shutter is that you have what we call active lighting, and this is a couple of different cases. One is extremely low light; you have no light. And in that case, then the image sensor, as I mentioned, can see what the eye can't see. You had near infrared LED. You need that kind of illumination. And the problem with that illumination is your eyes may not actually see the LED, but your eyes are going to perceive the LED potentially. And so if you were to blast that at somebody and they didn't know, you could actually blind somebody potentially. And secondly, in terms of power, you generally don't want to expose an LED for 100% duty cycle. So because of this and the fact that you have a very small limited time that LED is on, you need all of the pixels to be exposed simultaneously. So that's the one condition. And then the other condition is sometimes there are just objects that you'd like to penetrate with a deeper wavelength. And here's the case for driver monitoring where somebody's wearing sunglasses here. With infrared light, you can actually see through those sunglasses. So the three cases for the global shutter here: one is motion, two is in just extremely dark conditions, and then the third one here is really more related to the type of object that you're seeing. Now, one of the limitations that I mentioned before with the global shutter is this is a cross section of the pixel that I showed you before. One of the limitations is the additional circuitry, and where we actually stored that light after the photodiode has been exposed, as we call it, the memory element. Some people will call it the storage node. But it's subject to actually getting in parasitic light. If light actually gets into that storage node, it's actually going to cause issues. So what we do is we try to block light from getting into that storage node through all different types of, BSI, deep trench isolation, light guides, those kind of things, blocking light with buried light shields. So they're all different sorts of ways of trying to get this global shutter efficiency to improve. And here's kind of a good representation of what that looks like visually. So you're seeing here on the left a image sensor with poor global shutter efficiency as a result of the parasitic light, and you're almost seeing kind of like a transparent business card here. But this is going to, think about scanning barcodes, for example. This is going to result in, maybe lines that you're trying to scan that are blurred or a little bit close together. You could think about other areas of motion where, you get this kind of blurring effect, or you lose some sharpness, and it's difficult to image what you're actually imaging. So this is a key element of global shutter, is what we call the global shutter efficiency. Now, also going hand in hand with that is what, I mentioned the key case for global shutter is the active lighting or near infrared lighting. Now, one of the ways that we can actually improve the near infrared response of that photodiode is we can make the actual silicon that sits beneath the photodiode, we call it epi, thicker. And that means that the light can travel down through that pixel. And if it gets beneath the pixel, maybe it'll float back up into the pixel. So having a deeper, what we call epi, allows you to get better response at the near infrared. The converse of that, though, however, is the fact that that longer wavelength may now have penetrated into that thick silicon, but maybe it went into an adjacent photodiode. So what you need to do is you need to optimize that balance between what we call the MTF and the NIR. And that's something that generally, if you've worked with customers in the scanning industry or other industries where they've used NIR light, this is something that there are techniques in which you can get both, right? And that technique is a way to basically scatter light such that the light doesn't go beneath the photodiode, but allow that light to come into the photodiode. And in that sense, right, you don't lose any MTF, but all now you're doing is you're improving your NIR. So this, I think, is also kind of a key trend in the industry here, which is improving the near infrared response, and especially as you start looking at a lot more of the devices using infrared LEDs for their lighting. Okay, so that was a lot just on the imaging there. So some other considerations to think through: depth. So depth is becoming important in a lot of different applications, anywhere from machine vision to AR, VR to driver monitoring, etc. And one of the ways of doing depth, or a couple of the ways of doing depth, one is called indirect time of flight. This is literally just an image sensor where you are getting the response of different phases of light that are coming in. And by calculating the deltas between those phases, you're able to determine distance. So this is actually more kind of a traditional image sensor, but just different types of optics and depth calculation. There is what we call the stereo camera. And this is multiple cameras situated parallax, some distance apart. Can maybe get you longer distance, but the precision of it is a little bit more difficult. I think really the industry is balanced between these two right now. There's some challenges with indirect time of flight we can talk about, but I think longer term, right? You'd obviously want to move to one camera so that you don't need to. Frame rates, frame rates really fluctuate based on the types of different applications. So there's not one, methodology I could say here for frame rates. When you have fast moving objects, when you have, scanning or other types of specialty imaging, frame rate is critical. In fact, actually, if you get the frame rate high enough, you might not even need the global shutter because your frame rate's accounting for that motion. Um, Temperature performance is a big one in the sense that image sensors are very sensitive to temperatures, higher temperatures and lower temperatures. So the actual performance of the actual image sensor should accommodate that range in temperatures. And of course, we have cameras going everywhere now. And so our cameras are being exposed to a lot harsher conditions, low temperature, high temperature, sitting out at longer, running at higher duty cycles. And then the last one here that I want to mention is the color filter array. That was the kind of color checkerboard pattern that you saw on prior slides. And you have many different types of these as well. So a monochrome for active lighting is the way to go. You're not filtering out basically any light. And you don't need to because you don't really care about color. It's an NIR LED. It has no color information that it gives. You don't care. Or maybe, you know what, you don't have an NIR LED, but you just don't really care about color, then you go with monochrome because it allows the most amount of light in. There's certain types of specialty color filter arrays. Automotive is where you see this a lot, and they're really just trying to maximize for the different types of lighting conditions that you may have. So for example, classic one is this RCCC. A typical pattern would be red, green, green, blue. The red, clear, clear, clear indicates that you're trying to get some red information, but for the rest of the pixels within that photodiode, or subpixels within that photodiode, you're trying to get as much light in, basically a monochrome red. And then there are other kinds of tricks and techniques in terms of patterns. One that's also taking off is what we're calling RGB IR. And this is the capability of the single photodiode to grab red, green, blue, and then near infrared as well. And this is where you're doing a combination of color plus infrared imaging in the same camera. Traditionally, that's been the case. We can do that. It's just done physically through what we call an IR cut filter. But basically, it's an element that sits outside the lens that either allows through visible light or it allows through near infrared light. So it's a mechanical element that can actually be replaced potentially by something that you're doing on the sensor itself. Okay, so those are, and I know I went through that pretty quickly. These slides will be available, but those are a lot of the different considerations and kind of trends that you're seeing within the actual imaging part of the sensor. This next part, though, I think is extremely critical and oftentimes really overlooked. I think it's one thing actually that separates onsemi personally, but there are features that we can embed into the actual sensor itself, not related to necessarily the imaging, but more related to the system level that can really optimize for system level function. So classic case here, think about your doorbell camera. Your doorbell camera detects motion and turns on and alerts a user, hey, I've detected motion. I'm going to start imaging, streams an image to the person who's looking at it. That's one case, right? Another case could be a sentry mode on a vehicle. I think, Teslas have this built in where they detect motion and then all of a sudden the camera starts recording. Okay, well, in these systems right now, the way it works is that the ISP or the SoC is sitting there and it's actually looking to detect motion, or maybe it's relying upon a passive infrared sensor to actually do this as well. And because of this, you actually have a higher power processor that needs to be on to actually do the detection of the motion, or you have let's say, a more faulty PIR sensor that may trigger that ISP to turn on, but does it with false warnings. But it's something that we can actually do quite efficiently, actually, with image to detect motion. I'm not saying that we're classifying it or we're detecting types of objects, but we're simply just detecting the presence of motion actually on the sensor. And if you have the right architecture within the sensor, you can go into a very, very low power mode. Let's say sub 2 milliwatt type mode, leave the sensor on 100% of the time in that mode, detect motion, and then say to the processor, hey, wake up. And by doing that, now you've saved one, you've saved power, but two, hopefully the image sensor is a lot more reliable in terms of that detection than the infrared. And therefore, you get better detection and less false alerts. So at the system level, right, this is what I'm talking about. It's designing a function in that really serves the overall benefit of the application. In the case of even the one I'm talking about here for a line of our sensors, here's kind of a classic case where I think people that have used like an Amazon Ring or any doorbell camera, they look onto their cell phone and they see little areas where they hit on where they say, you know what, I don't really care about motion in that area because, you know, somebody's over here in the bushes or maybe somebody's up here in the sky. I don't really care about the motion, but I care about the motion that happens right in the middle there. So those little boxes that you see are X'd out. That's done on the image processor. But in addition to being able to detect motion, we also have the ability to detect within our sensors where the motion occurred. So rather doing this kind of function on a separate discrete processor, this is actually something that we can do on the image sensor itself. So here we put one of our 4K sensors into a VGA mode, 1 frame a second. We've blocked out areas that we don't care about. And suddenly, when we've detected motion, we go back to the processor and we say, hey, processor, we detected motion. Processor says, oh, hey, okay, it looks like there is something important here. We switch into the 4K mode now. And in that sense, right, you're drawing a lot less power than you would traditionally if you had been relying upon the actual processor being on the entire time to detect motion. So you could really extend your battery life here. Or, you know, in the case of other scenarios, just power for whatever, you know, maybe that camera is. In addition to that, you know, one thing that you don't see done very well traditionally in image sensors is scaling of that power based on the resolution and the frame rate. And the reason is, if you think about like a handset, mobile handset, your handset is on for a very short period of time, typically when you're taking photos or you're taking videos. So the need for you to really scale down to lower resolutions and have a very low power mode, except for maybe your standby mode, isn't really all that critical. But if you've got a sensor that's sitting there and it's running 100% of the time, you'd like to put it into a very low power mode that is going to draw the least amount of power. And you know you can turn off elements within the sensor that don't necessarily need to be on when they're not being used. And so we've developed some mechanism around that ourselves. But I think this is one of the trends for improvement here in the industry is getting power that actually truly scales with the actual resolution and the frame rate and doesn't kind of saturate to some point. Another function that is simpler for us to build onto the sensor, and I'll kind of explain it here. In the video conferencing space, oftentimes what you have is a big video conference room. And of course, you want to see everybody in that room, but you have somebody talking. Maybe some motion has been detected or a microphone has picked up that somebody has talked. And now you'd like to zoom in on that person talking. Meanwhile, it's still like the full image itself. Okay, so the way that that's done is you're taking traditionally you're taking that full image, you're transmitting it to the processor every single frame. That processor is probably storing that image in some sort of memory, and it's now going to scale and crop maybe a couple of different images or maybe even more. And so it's going to do it at its level. And you're taking processing power to do that. You're taking memory and, of course, time. Now, having said that, this is something that you could actually do on the sensor very efficiently. So I'll give an example. We have a sensor. We call it the AR2020. It's a 20 megapixel sensor. It has what we call a smart region of interest function built into it. So on one data path, it's got a scaler and a crop. So effectively, you could scale this image down and crop it to, you know, let's say a VGA image where you've got the full field of view. And this could be user definable. Maybe it's 1 meg, maybe it's 2 meg, maybe it's 5 meg for God's sake. But then in that region that you truthfully care about, you want to get that negative 20 megapixel type resolution in that area. Okay, so Now you just kind of crop to that area that the processor has told you, hey, this is the area that I truthfully care about. Just give me only that part of the image. Okay, so what we did here, in effect, right, is we took a 20 megapixel sensor and we made the readout and therefore the processing power go down by 15x roughly in that range, right? So a couple of benefits here. One, that processor, if this is really what you're trying to do, that processor may not even need to necessarily process 20 megapixels. Um, and certainly not at every single frame if it is going to do it. And what that means is that you may be able to use a lower cost processor that doesn't need to do 20 megapixel. But furthermore, even if you have a pretty high end processor, you're still saving bandwidth, you're still saving power. And again, this is something you can do very efficiently on the sensor itself, whereas it's being done on a processor right now. So this is all about just understanding the customer application and things that you can do actually on the sensor that are, maybe not imaging related per se, but they're complementary functions that add value within the system. And so if you're repurposing a 20 megapixel camera that had been used in a cell phone into something for video conferencing, or you could use this in security surveillance, for example, you may not have that function built in. And so you're taking in every single frame, 20 megapixel, you're processing it, you're storing it in memory. So this is a function that we've built in that you can do real time, frame to frame, no latency, and completely user definable. All right, so that I think is kind of an example there of more of what I'm talking about when it comes to system level functions. And really, again, it goes to the image sensor vendor who needs to understand what the application is and really design features around that. Go to the customer or groups of customers and understand what their pain points are and define your sensor around that. I think the prior way, having a 20 megapixel sensor, that's really on the high end right now, but this is a way that we can effectively take that 20 megapixel high end sensor and give you 20 megapixel, but you don't need the processing to actually do it. All right, so on to kind of my next slide here, which is the fact that I've showed you a lot of things. I've showed you a lot of different techniques when it comes to dynamic range. We've talked about resolution. We've talked about optical format. We've talked about low light capabilities. We've talked about complementary functions. So the exciting time for us right now is between 2023 and 2024, we have 13 different sensors that are actually releasing, ranging from the low power family, which we've already press released if anybody would like to look up, our low power, high dynamic range technology sensors that we've already released one particular sensor, but we have a couple more on the way. The Hyperlux original kind of branded sensor, which we did for primarily automotive, but this achieves a dynamic range all the way up to 150 dB, compensates for LED flicker, has a couple of different resolutions. Global shutter sensors that I've mentioned, we're working on those. And we'll have a release probably coming in the next couple of months as a little bit of a teaser here on some newer products that we're doing. And then finally, a really exciting area that we're getting into is this depth and indirect time of flight. So again, you'll be seeing more and hearing more about that. If there are questions or information, or you want to talk to us about that, feel free to reach out to our sales, and hopefully they come into myself and marketing, and we can provide you more info. But you are going to see this coming publicly here, also as a teaser in the next couple of months. So what does that mean, right? It's all of these different requirements, all of these different applications. You just can't squeeze one sensor into it. It's going to have to come from multiple different types of sensors. And so we believe with this kind of range of sensor portfolio that we have, that we can cover pretty much any single application that you have, from resolution to size to performance and dynamic range, low light, and even motion. So the other thing that I would like to mention here too is this family-based approach. It's really nice because every sensor traditionally has been different from another sensor in the architecture. So that means the registers are different, the way that it operates are different, and the engineers have to relearn every single image sensor. The benefit of having a family approach is that that sensor is fundamentally at the heart the same exact sensor, except for we have it in a different resolution and optical format. So you get more bang for your buck in the sense that you've really designed with multiple sensors, even though you just designed with one sensor, and now you've allowed yourself to scale. You may have to rewrite your driver, do some small amount of image sensor tuning differences here, but for the most part, fundamentally, it's the exact same sensor. Um, and so I'll leave everybody with this slide that will come, of course, with the presentation. But we kind of categorize industrial and commercial viewing into quadrants, and we have design wins with the leaders in 25 different areas. But I would say that the term that IoT that people used to use, let's say 10 years ago, wasn't really well defined, has now actually become quite defined. And there are a lot of different applications and verticals that are emerging here that you see. So industrial and commercial, we break it up into viewing segments, we break it up into machine learning segments. The industrial segments are going to be just more of the kind of higher end type cameras, ruggedized. And the discerning difference here between the viewing camera and the machine vision camera is that the viewing camera is obviously for the human eyes. The machine vision camera is doing an operation, scanning a barcode. You don't need to see the image, it's just doing the function. And similarly, you have kind of the same thing here on viewing images, or sorry, not viewing, but commercial side of things. So, a commercial machine vision, maybe access control, where, it's a doorbell camera where you're looking at a face and granting access, or an AR VR camera where it's processing maybe the map of where you're at. You don't really care about it as the user, but certainly it's important to the AR VR. And I think the trend that we really see is that more and more of the viewing applications are bleeding into machine vision. And so there's this line in the middle here that you're seeing devices moving from left onto that line, where maybe it was a traditional application that you use for viewing, like a security camera, for example, right? You used to classically see that person sitting in front of a monitor and looking at all the different images. Well, now you may embed machine vision into it to be able to detect people, and other things that you actually care about. So I think there's really a trend of moving from left to right, more and more integration with machine vision. And you could go a little bit from left to right. All right, so last thing here, just other considerations, and this is quick, I'll wrap it up, and then we'll get to hopefully the Q&A session here. But the other considerations are things like functional safety, sensor in literally or life jeopardizing type applications, automotive being one, right? So you may build redundancy and fault detection into the actual sensor. Yet, and there are actually well-defined standards for this. It's ISO 262 for automotive, and for robotics, there's another standard. You can imagine, a robot on a factory floor, unconstrained. Somebody walks right past it, bam, gets run into. So the classic type of operation. And so building redundancy and fault detection into the sensor is critical for these type of applications. Reliability. It's a lot different to be a cell phone camera that may be on a small percentage of the time and versus a security camera that's on 100% of the time. Of course, that's going to reflect the reliability and the lifetime of the actual sensor. So you have to take that into consideration, as well as how long is your product going to last in that marketplace. The ecosystem is extremely important. I spent 8 years in automotive imaging, doing ecosystem primarily. And I would always say, as I start out a meeting, that you could define the world's best image sensor, the best low light capabilities, the high dynamic range, the highest resolution. But if you didn't have a processor that could actually process it, it's just going to collect dust. Similarly, you could say the same in the optics, that if you have a really great sensor, high resolution sensor, but you don't have the optics to actually resolve, then it's pretty much a worthless sensor, right? So we have to be in lockstep with our ecosystem partners. Even in addition to that, I would say that if we're working with them ahead of time, we can understand their pain points and define in features like I showed you prior. The other element of this too is, getting that driver and tuning done. Maybe that's one element out of your design that you can kind of check off, and maybe you could do a little bit of tweaking here on the tuning. But we've given you something that's pretty much ready to go. The next one here, I don't think I really need to mention after COVID, but Availability and having a robust supply chain are, of course, critically important, as is the worldwide support. And I think this gets underrated a lot, but having a distribution network and having field applications engineers and people that can support you on site, regardless of whether you're a high volume customer or low volume customer, is important. And furthermore, it can't be a high touch that we give you the tools and we give you the documentation. So again, things that are just not related to the product, not really related to the actual imaging part of it, but are critical in considering your design. And then the last thing that I mentioned there is this family approach. The fact that you choose a family of sensors and it allows you to scale with the different types of devices you have, and you don't have to keep relearning sensor after sensor. Okay, I need an 8 megapixel and a 20 megapixel, and they're different sensors. So being able to scale and have a family-based approach to the image sensor design really allows you to improve your time to market. I'll skip over just some slides for the sake of time here, but something that we're actually doing at onsemi is something we call PRISM, stands for Premier Reference Image Sensor Module. We effectively are, as a part of our design process, we are developing modules for our image sensors. Now, I want to make it very clear, these are not for sale for production. These are not production units. But what they are validated units that have image performance tests done on them that can be used for development purposes. They all have a same connector, can plug into a development board, could plug into one of our partner ecosystem boards. But the whole goal here is to give you something that's more realistic for your evaluation purposes, and then maybe even helps your evaluation purposes. So I say that because we have adapters also. It's not just actually the module itself, but we have adapters that allow you to go into some of these partner platforms to help you develop a driver, to help you tune, or, for that matter, if the driver and the tuning exists, to get you up and running and streaming right away. Because it has the same connector, you can also try out many different sensors on a partner platform. Vice versa, right? You could try out one sensor on many different partner platforms. And then finally, this approach really allows you, if you don't have a lot of experience in developing a module, you can come to us and you could say, hey, do you have any recommendation on who to use for this module? And we would, guide you in that path. Or, we could guide you even through a distributor who may have taken what we've developed here, and simply made it at a level that is production worthy. So again, this is, for prototype type volumes, but can potentially turn into something production volume with your own modification or with the help of a distributor. So at the tools level, we believe additionally that this is going to expedite your time to market. It's going to help us out in terms of being able to connect into these platforms, and it's going to help you out because it's going to allow you to get the streaming on a processor platform almost instantaneously, hopefully. So with that, I will skip over this. There's all sorts of collateral and deliverables that come with the module. But with that, hopefully in the 50 minutes that I've used here, all of these terms that you've heard, that I've mentioned here, that we've been able to provide you with some sort of clarification, or you can think of us, certainly if you do have any other concerns or questions. And with that, I will throw it over to Jenna for questions.
Thank you, Steve. Yes, let's move on to the Q&A. Just a reminder for our audience, you can submit your questions using the Q&A tab to the left of your screen. We do have lots of great questions already, so we're going to try to get to as many as possible. So this first one, Steve asks, where do you see global shutter being used the most? And do you see a shift to rolling shutter?
So I mentioned this earlier, but I think really it's in, more than anything, actually, probably more in the active illumination. So in really dark scenarios, or scenarios where you want kind of deterministic, what the light is going to look like, kind of scenarios, this is where we need global shutter to align with that near infrared LED. I think that's number one. Fast motion, believe it or not, is probably not as much of a concern as you would think. Even in automotive, right? If you look at where the global shutter sensors are, they're usually in the driver monitoring with the infrared LED. They're not on the outside of the vehicle. So it's not to say that it's not needed for really fast moving objects, but probably more in the lighted infrared. And to the final question there, rolling shutter still has some disadvantages in the sense that, the difficulty of aligning to the IR LED. So I think, hopefully at some point, or, likely at some point it'll transition from all global shutter to rolling shutter, but, I don't see that in the next horizon for probably at least 3 or 4 years.
Understood. Thank you. The next question asks, you briefly mentioned depth. What are some improvements you see coming in the future, as there are many issues currently with speed of objects, distance, etc.?
Yeah, I didn't get to talk too much about that just because of all the topics that were here. But the indirect time of flight has issues with speed, um, rapidly moving objects, and the reason because effectively you have. I mentioned you have to capture different phases. You generally capture, let's say, 4 phases, and then calculate the difference. Well, that's typically done off chip by another discrete component. And the time to do that means that if there is motion, you have issues. Additionally, there are issues with distance. Distance is sometimes troubled by the fact that you may get infrared illumination from the sun or other IR sources that may provide noise. And so at longer distances where in depth you've relied on IR LEDs or pixels, on longer distances, the IR noise gets to it. And so you want to find a better way to make sure you can get better depth, and longer depth, further distance. So I would say those are kind of the two at the top. And, maybe keep your ear to the ground here. There certainly are some developments that we're working on with that space.
Excellent. And this will be our final question. We had a lot of great questions today. Couldn't get to them all, but we will try our best to get back to everyone who submitted a question personally after the webinar. So this last question here, Steve, where can I get more information on this prism concept you introduced? Would it be helpful for my design?
Yeah, so we haven't really talked about it too much publicly. Actually, this was kind of an introduction to it for people here. So everybody sitting here actually got maybe a new piece of information that we haven't fully released. So appreciate that. It's a little bit early in its conceptual phase. But having said that, actually, all of the sensors that I showed on here actually do have a prism module. So for more information, what I would say is contact your local sales or distributor. Certainly, you've been introduced to it through me. I'd be happy to connect you as well, to anybody myself. But we think it's really going to be something powerful that will change the way that you develop, and really hopefully give you an evaluation platform that is in the real world, allows you to get up and running and streaming quickly, and maybe even serve some purpose for production design.
Thank you. Great. Well, this webinar has been recorded. You can access the recording within 24 hours by using the same link you received earlier. Thank you for joining this Fierce Electronics webinar today, and we look forward to seeing you at future events.